it's much easier to explain it because the signal is one-dimensional. But before I talk about it, remember the unsharp masking or high boost is, as I mentioned, if A equal to 2, okay, is the original image plus high pass. Original image plus high pass. It's a so-called high boost or unsharp masking. Now, take a look here. Suppose this is the original image, okay? We have an original one-dimensional image. And then if we go for the low-pass signal, okay, or filtering, then the dashed line here, okay, is the original signal. Okay, now it has been smoothed, right? So you will see the corner right here, the sharp corner right here, right? That's low-pass filter, so that we can smooth the sharp corner. Now, this is the result of high pass, okay? High pass. A high pass is what? Is original minus low pass. So the original, this is the original, and minus the low pass. So the result will becomes this one. See that? Right? The original, the value is lower compared with the smooth one, right? At the same location, so you will have the negative, a negative value, right? But what about this one? It's the original, okay, value at the same location here minus the smooth value, then there will be the high pass filter. That's what I keep saying, you just might calculate the difference, okay? So this is the smooth signal. This is the high pass signal. Now, let's take a look. What about the unsharp masking, okay? This is original signal. And this is what? This is the high pass. This is the high pass. Okay? Everyone follow me? Okay? Now, the unsharp masking is the original signal plus the high pass. And this is the final result. Here. This is the black line here is the original signal. And this, after we apply the unsharp masking, the final result will goes like this. The red line here. See that? We didn't change the smooth area. However, we intensify the difference along what? Along the edges. Okay? See that? 我们就不止旁边的这些比较smooth的我们不会去动它，可是呢，在这个 edge 的时候呢，你看低的让它更低，高的呢让它更高 ，so that we can intensify the minor the details, okay, of the image. That's the purpose of unsharp masking. Okay, all this operation is based on the filter. Okay, based on some base filter. So just remember the terminology. Okay, low pass filter, high pass filter, Laplacian filter, unsharp masking. Okay, then you can call for the OpenCV to do different kinds. You can take this operation as the pre-processing. Okay, of course sometimes you can use as the post-processing, especially you apply a deep learning model to output an image. And after that, you can do something like this. Okay, so no matter you use as a pre-processing or post-processing or before. Okay, so any question about the convolution approach or the filter design for image smoothing, sharpening, or unsharp masking? If you don't, let me say something more. Okay, I should have skipped it, but because if you want to do it by yourself, here's just the result. Okay, for the medical image. Okay, this original image, this high pass filters, you see that it intensifies the edges, okay, and this high boost, okay, this high boost will show you more details. Well, actually, well, after the high pass, you might apply the CDM. Okay, for example, you can apply CDM to further intensify the details. Okay. Let me say two more things. Okay, I don't have too much time, but I want to show you the similarity with the minship, because you are now working on the assignment number 2, so you might have a good idea or experience. Okay, here's another tip. That's for edge preserving smoothing. For edge preserving smoothing, you can find this algorithm in OpenCV. Okay, they are all the same. Minship we already is one of it. Okay, and the other one I'm going to talk about is bilateral. Okay, filter. Okay. The other one is by diffusion. Actually, there's called anisotropic, okay, diffusion. It got the idea from the heat transfer. The heat transfer, it will transfer the energy from high temperature to low temperature, okay? Then someone used this idea for image smoothing, okay, to smooth something with so-called diffusion and isotropic. It means all direction, just like transfer the heat, right? High temperature, it won't go in one direction, it will go for all direction. Okay. Isotropic means just one single direction, but this is, and isotropic is all direction diffusion. I will introduce this, and you will find the similarity compared with minship. And which one will be the best depends on your application. Okay. So anyway, after assignment number 2, you can learn something. But let me say this: bilateral. Okay. Why called bilateral is when you take a look, it's nothing but a mean. It calculates the weighted mean. See that? I is the graph value or the color. It doesn't matter. It's the color image or graph scale image. Take a look. Then omega here is the neighbor. Then you have to define the neighbor. Okay, 3 by 3, 5 by 5. As I mentioned, if you use a very large neighborhood, then you might over smooth, okay? So it depends on your application. Anyway, you calculate, then the weight is given by these two functions, one called FR, the other called G of X. Okay, let me finish it here. Okay, W here is nothing but just to normalize. Okay, we just to normalize the value. Okay, so anyway, you can think of the bilateral filter is nothing but a weighted average, and the weight is determined by these two functions, FR and G, and then it depends on what. See that? The difference of the color, or the difference of the intensity. See that? X, that's the center we want to smooth. And Xi is defined by its neighborhood window. So what will be the similarity compared with the mission? This is something to do with what? Color. Okay, there's something to do with color. And take a look, we have another function, okay? Then the weight is determined by what? The location, the distance between its neighborhood Xi and X. in the center of the window. So G is something to do with what? The spatial information. All right? F, something to do with the color. G is something to do with the distance. So that you can infer this to your meanship operation. Okay? Then what is F and what is G in the bilateral filtering is, okay, it can be a Gaussian or it can be a rectangular kernel. Okay, let's talk about the Gaussian because we use this a lot. Okay, a Gaussian kernel. A Gaussian kernel is like, I put a note here. Okay, here is the Gaussian kernel, right? The weight is given by FR and GS. Then if we use a Gaussian function for F, then this will be its mathematical equation, right? Then that's the difference of graph value. Okay, IJ and KL is the center. Okay, it's the center of the window, which means we are looking for. Suppose now we are looking for the pixel at coordinate KL. Okay, then IJ will be its neighbor. Okay. No, I'm sorry. IJ should be the center. Okay, and KL will be its neighbor. Okay, its neighbor. Okay, what's that? Okay. So this is based on the Gaussian distribution. Okay, for color difference. Then the second one is another Gaussian distribution based on the distance. Now, it got two parameters. The first one, just exactly like the meanship, which is the bandwidth for color. And the second one is what? It's the bandwidth for the spatial distance. That's it. Okay, so similarly, they are the same, but the idea a little bit different. Okay, a little bit different. And which one will be better? I'm not quite sure. Okay, but anyway, that's how we get. Okay, and this one can be write down as because we have the multiplication of two Gaussian function, right? A two Gaussian function, then it can be write down as this term. We can use one, just one. Okay, exponential function, right? Right? Everyone follow me. Okay. Exponential. We can write down as A plus B, right? Okay, the same here. Okay, so we put them all together. But again, we still for the user still need to determine what should be the bandwidth for the color or intensity and the bandwidth for the spatial difference. That's it. Okay, that's it. So for the user, you need to determine the bandwidth for color, for distance, and you need to determine what should be the window size. Okay, what should be the window size? 好，这是你那个 window 视窗，它的 neighbor. Okay, what you have to look for. Okay, this so-called bilateral. Okay, bi means two. So we look for the color difference and the spatial difference. Okay, here. Okay, so it's simple and well, actually, if you want, you can write your own programming code. But anyway, OpenCV provide this. So whenever you have a chance to use this more complicated algorithm for image smoothing, that's the edge preserving smoothing. Okay, 它们都是 edge 啊，它会保留 edge. You will remove the noise but preserve the edges. So you can go for the meanship. You can go for the bilateral. Okay. Okay, and finally, as I mentioned, it's nothing but just a weighted average. Right? It's a weighted average. The weight is given by the bilateral. Okay, so that's it. So here give you the example. This is the original image. Okay, look at the more noise or complicated graces in the background. And this is the Gaussian. Everything is blurred, right? Everything is blurred. And this is the bilateral. Okay. Now the grasses have become more uniform here, but I mean some detail are preserved, but not the all details as good as the original one. But that's the result of bilateral. Now let's take a look of the next example here. That's for color. Okay, this is the original image. And this after we process with the bilateral filtering, okay, you can see that now the skin getting more smooth, right? Okay. So a lot of the image processing tool with your smartphone they provide. I didn't say they use this technique, but you can use it to change the color scheme. But what I want you to focus on is, take a look here, the fine thin hairs right here. See that? Yeah. They are retained. Okay, they are retained. Okay, it's very thin, very fine. Okay, but we didn't make it. Okay, we didn't remove it by lateral filtering. But take a look very closely, appearing the skin color, it looks better, right? Especially for a young lady, they prefer they have a picture like this instead of this. So bilateral filtering. If one, you can also try out the dimension and see which one will give you the best. Okay, bilateral. Now the other one, that's one saying here, anisotropic diffusion. Okay, again, it's also used for age preserving smoothing. Okay, age preserving. It can smooth the background, smooth the noise, but it can preserve the edges. Now here's how, as I just mentioned, is based on the idea of heat transfer. Okay, 它是那个热流啊，它是热传导。Okay. You will transfer the high temperature or the energy. You will transfer the energy from high temperature to the low temperature. Based on what? Based on the gradient. Based on the gradient. Okay? Based on the gradient. And you can take a look. The C here is nothing but the coefficient. Okay? The coefficient. So here the div means divergence operator. Okay? And delta I is the gradient, okay, the gradient, which means that when all the heat transfer, okay, it will go for the direction that will give you the minimal changes of the temperature from very high temperature to the lowest temperature. That's the so-called gradient, okay? If you don't like this term, the gradient is the difference, just the difference, okay? The difference in a digital image. And C is the corresponding the so-called diffusion coefficient, okay, the weight. Now, the weight is also a function of the gradient. Okay, I will show you how the original model work. Okay, I skip a lot of detail because this is almost the very first author that proposed this anisotropic diffusion. Okay. For image smoothing, this is the two last name of the original author. Okay, we call it PM algorithm. PM algorithm. You can look, you can find it from the OpenCV. Okay. Now, here's how we do the smoothing. Okay, this is the original color or intensity. Then plus is diffusion. Then y divided by 4 because it looks for the 4 direction. It looks for the 4 direction. This is the actual one. okay, x, y. Then it look for its north direction, west direction, east direction, and south direction. That's it. Okay, it look for this. Of course, you can say why not this 4 direction. Of course, you can do that. Okay, but in the original proposed algorithm, just look for its 4 directions. Okay, then you calculate the difference or the gradient in each direction, and then it's quite easy, right? It's quite easy to calculate the gradient, okay, in these 4 directions. Then times the corresponding coefficient, and so if xy is an edge point, then you won't do anything. Let me say it again. If xy is an edge point， 假如 xy 它是一个边缘，它是一个物体的边缘点，很重要。It's a very important, okay, edge point. Then in that case, C should be very close to 0, which means it do nothing. It will retain the original edges. But if xy is some not important or background point or noise, then you will smooth with respect its 4 neighbor by the gradient, which means if xy is not an edge point, then you will do the smoothing with a larger coefficient value of C. That's the whole idea. That's it. Okay. Now, how it works to calculate the gradient is very simple. In digital image, that is how we calculate. Okay, 1, 2, 3, 4. That will be the 4 direction. Then this is the direction in the north. Okay, and for this one, you will have the direction of y minus 1. Okay, suppose we scan the image from the upper left corner. Okay. We just simply calculate a color difference or grade level difference, okay? And this will be the difference, okay? The second direction will be in the south here, okay? That will be x, y plus 1. And the third direction will be the direction on the right here. And the last one will be the direction on the left. That's it. Okay, we simply just calculate the intensity or color difference. Okay, then C is the diffusion coefficient. It's something to do with the gradient. Okay, the requirement is so it per C should be some function. Okay, with respect to the gradient. Okay, now. If the gradient is 0, then we expect it has a very high value of 1. Okay. Otherwise, we expect the value, okay, to be 0. That's it. So, in the original idea, g function is simply given by this one. Okay, it's inversely proportional with respect to the delta I. With the gradient, but again, in the user defines some constant k, okay, k. Even in the heat transfer, you need to define the temperature. What should be the temperature you want to reduce? Okay, that's something like this. Okay, k is a constant, which is defined by the user. Okay, so then the g value, the g gradient will be you will have the sum. Okay, it's a non-monotonic decreasing. So if the delta I, which is the gradient, is very large, then the corresponding g will be equal to 0. Okay, which means what? If delta I is very large, means it got to be an H point, right? So that the gradient will be. Just I mentioned here, okay, the H point, the gradient will be large, very large. For the background or something inside the edges, the value, you won't see too much changes here. So the value will be 1. When it's equal to 1, it means what? You need to smooth. You will smooth with respect its neighbors. That's the idea. But this does not have to be the only coefficient function. There's a lot of inference model, okay? But this is based on the PM model, okay? And the only thing for the user is you need to justify, or you need to fine tune the constant k, okay, with respect to the delta r. That depends on what is your original input, right? If you want to change, if you want to make a larger change with a very small delta I, maybe you might use also a very large k, or vice versa. That's it. Okay, it needs some experiment to that. There's no easy way to determine the value of k. Okay, so once you have, then we can go back. Okay, we can calculate the gradient based on the difference in the four direction, and also once you have the gradient, you can calculate the corresponding coefficient, and then we take the mean. Let me say it again. If x, y is an edge point, then the coefficient will be very close to 0, which means we do nothing, we don't do any smoothing, so that we can preserve the details. Okay, and if sy is the background or inside the edges, it's not an important edges. It's nothing to do with the details. In that case, we will smooth with respect to its neighbor. And we need to, sometimes you need to do this many times. As I mentioned here, see that? It's set t to be 0, which means the original input image. And we go for t equal to 1 and 2 and 3 and 4 and more. Okay? So in near iteration. Okay? It doesn't, we don't just do it for once. Okay? We need to do it for several iterations until the result will satisfy. Okay? But again, if xy is edge point, no matter how many iterations you apply, it will retain the same, but you will smooth the background or the noise, okay, in each iteration. Okay, that's the whole idea. This an example here, the Chinese paragraph. This paragraph was written around 7th century, okay, which means more than 1,400 years ago. You can see there's some of the background, okay, has been corrupted a little bit, okay, over time. And here's the result. You can see the pattern, okay, smooth the background, however, but it retains the details of the paragraph, okay, of the Chinese character. So that's an example. And just show the more details, okay, how you preserve, okay, the details. Okay, so that's so you can apply mixture bilateral and isotropic diffusion, okay, but all depends on what? The color difference, the spatial difference. Okay, so that's it. That's the idea. And which one will be the best, and which one, in terms of the effectiveness or efficiency, then depends on your application. Oh, here show you the effect of K. Okay, as I mentioned, the K is right here. Okay, K here. Okay, you measure how are you going to signify the gradient. Okay, K. So if K is getting larger, you see that the fine details are removed, right? The details are removed if K is quite large. For this example, I didn't say whenever K equals to 13, it depends on what is your input. Okay, this a K, I didn't show up the original image. This a K equal to 1. Okay, so this mathematical image will show you some. Okay, K equal to 5. So when K is very large, it might over smooth the details. So it depends on what's your purpose for this application. Okay. So that's it. That's about the image smoothing, image sharpening, okay, with convolution filtering, and or by using the more complicated age-preserving mean-shift bilateral filtering or anisotropic diffusion. All depends on two factors. One, color, the other one, their spatial relationship. Okay, that's it. So for the user, no matter what, you need to define what should be the window size you are looking for. Okay, the window size you are looking for. Okay, so that's it. That's about image smoothing, image sharpening. They can be, when you go with the deep learning, okay, it can be used as a pre-processing. When I say pre-processing, is you apply it to the input image and then to the deep learning model. When I say post-processing, then I say it applied it to the output of your neural network, okay? So we can use both as a pre-processing or post-processing. That'll be fine. For intensity image, or even binary image could be better for our next topic, okay? Morphology. So it can be applied for intensity image or color image. That'll be fun, okay? Okay, any questions before I go for the next topic? Okay, if not, then let's talk about morphology. Okay, it's also a very important topic. Again, it can be used as a pre-processing or post-processing, especially when you incorporate it with the neural network. Okay, very important one. Remember when we talk about the Schooner's normalization, okay, right here, Schooner's norm, for the binary image, after we do the normal transfer, see that, I mean, okay, this is good enough. Okay, you can see a lot of pattern, right? A line pattern here, as I just mentioned before, because the transformation is now one-to-one corresponding. Okay, it's a many-to-one, which means many pixel point where after the transformation they will point to the same location. 就是它这个不是一对一的转换，它转换的时候呢，有很多点会转换到同一个点。So some of the point will be missing. Okay. It does not fill with line, but you see the white line here, they are the background. Okay, they are the background. There's no corresponding point from the original pixel right here. That's because we are talking about the discrete, we are talking about the digital image, that's the reason. Now, if we want to use it for some further processing, then we need to, you can try out morphology, for example. Okay, so let's talk about the morphology in binary image first. Okay. Okay. Morphology is something to do with the set theory. 它跟集合论有关。But don't worry about the mathematics. Okay, I will make it simple for you to understand. Not exactly the same as the original mathematical definition, but practically that can be implemented, okay, very easy with your programming code. Morphology. We're starting with the binary morphology, which means what? You need to apply thresholding first to convert, okay, no matter color. If we go for the color image, you need to convert the color image to the grade level image. And then the grade level image, by thresholding, then we can convert it to the binary image. We're talking about a binary morphology. Later on, we will expand it to grayscale morphology, okay? And some people further extend it to color morphology, but we don't have too much time. I will talk about the binary morphology and the ground level morphology. 这个 in Chinese 他们叫形态学 ，okay? Morphology, something to do with the set theory. 它跟集合论有关。Now, let's take a look at how we define morphology, especially binary morphology mathematically, okay, with the set theory. Now, the first operation of morphology is called translation, okay? Translation. That's how we define the translation. Suppose A is original input, okay? A is the original input, original binary image, okay? A is original input. Now, we transfer it by T. We transfer by T. The notation, we put it A sub T. T is the translation, okay? The translation is only the shift the pixels, how many pixels is shift, okay? Now, suppose A will be all the elements, okay? A is all the elements that belong to big A is the image, okay? Original binary image. A is the element, okay? Now, we convert it to A by T, then we will have the new, okay? We transfer, after transfer, then will becomes nothing but A plus T. Now remember, A is not the graph value. A is not the graph value. A is the location. A is the location of the binary image. We're talking about the location. We are not talking about the graph value. Don't mix it with the image smoothing or image sharpening, okay? 来 A 指的是它的位置 ，okay, pixel 的位置 A is the pixel you translate, okay? You shift or translate, okay? So we put A plus T, okay, for all A that belong to A. Okay, let's go so-called translation. The so-called translation. Okay, so the operation by definition is based on the set theory, but eventually we don't need it. Okay, just mathematical. Okay, we make it formal, especially when you read the textbook or when you read the paper. When you talk about the morphology, you got to know how. By definition, okay, by mathematical definition, how that works, okay. So everyone follow me, yes, okay. The lowercase a is the element, okay, of the set A. A, when I say set A, I mean A is the image, okay. A is the image. Now we transfer the original object, okay, by T. Okay, that's called translation. Now, you know what does it mean for translation in morphology? Then there are 4 basic operations in morphology, and basically all the combination are these 4 basic operation. Actually, I should say just two operations. One is called dilation, the other one called erosion. Okay, and then we have open and close. These are the four basic operations in morphology. Okay. Well, actually, for open or close, they are nothing but the combination of dilation and erosion. We apply dilation first and then erosion, or we apply erosion first and then dilation. Okay. If know what is the meaning in English, what does it mean by dilation or dilate? 可以，还有没有更好的词语 ？Dilate means to getting bigger, getting larger. 膨胀，对，就是膨胀，它就是膨胀。Okay, it's something to do to growth, to expand. Then what is erode? It got to be 不是膨胀的话，当然 right to shrink, to reduce, to shrink, to reduce. That's it. That's all the purpose for dilation and erosion. So for this one, it's to growth, to getting big. Okay. Actually, right here. Okay, to fill, to expand, or to grow. Okay, to expand or to grow. Or to grow. Erosion is to reduce. Okay. Or to shrink. That's it. Okay. That's it. That's all the purpose. Now, let's take a look by definition, by mathematical definition in morphology is like this. Here's the notation for dilation is A. Okay, we use this notation. Okay, a plus sign inside a circle is the dilation, which means when we use a plus, is to growth, right? Then you know for erosion it got to be a minus to reduce. That's it. Okay. Now let's start from here. This is the responsibility of the user. You need to define B. B is so-called structuring error. Okay, this is called structuring error. Okay, sometimes we use SE. Okay. So A is the image. A is the input image. Now we are talking about the binary. Okay, it's the image. Then it dilate. This image is dilate with respect to the structuring element. So it's nothing but by this definition will be all the element is A plus B. For all A belong the set A. And for all small b belong to the structuring element B. Okay, that's it. And you know this means what? It means the translation. So it means what? We translate A for every possible structuring element defined in B. Okay? Let me show you an example. It would be much easier for you to understand. Let's take a look. If this is A, okay? If this is A, and this is B, the reason I say later on I'm going to give you an easy way for the dilation morphology. That's because the result could be a little bit different from this. It's mathematical definition. For the structural element B, okay? So first, for the user, you need to define what will be the structuring element. You can think of it as a window, just like what you do for average, okay, or sharpening. It's a window. 它是一个视窗. But you can define any shape of the window. It does not have to be 3x3 or 5x5. You can have a window goes like this. You might have a window like this. But for this application, I don't know. I should not use this one as an example. For this one, you have two parameters. The first one, you need to determine its size and shape. Okay, the user needs to define the size and the shape. Okay, it could be the size like this, or it could be the size of 3x3. It can be a 3x3, it could be a 5x5, okay, anything else. And the second, you need to define the origin. Where should be the origin? It will be different. For this case here, you define the B at origin right here, or the origin right here will be totally different. Okay? You can put the origin right here, or you can put the origin right here. When I say origin, is this origin should be aligned with the image A. So for this case here, the origin, you put it here, then it will come. This is the pixel in A. Then you need to do something for the remaining element. Or if you put it here, see that? If I put the origin here, then it will think of these three neighbors, right? In the lower row. But if I put the origin right here, then you will think of these three elements. One to the left, one to the right, one to the above, on the top. So it will be a little bit different. The shift, because each one is a shift, a translation. 每一个点都是一个位移。所以呢 for this case, if I put an origin here, it means what? It will shift to the low, okay, to the lower location, and lower location to the left, lower location to the right. But for this one, it just to the neighbor, to the left, and to the right, and what? A pixel above them. So the translation is a little bit different. Everyone follow me? Even the shape or the size is the same, but if we define it with different origin, then things will change a little bit. Okay. Usually, we don't define a structuring element like this. It say the center is the origin, but this one is not an object point. Usually, we don't do that. We don't do that. Okay, remember. For B, we will take it this form. We won't keep it empty. But it's legal to do it. But usually we don't do something like this one, okay? Usually we won't set this will be the center, and the center is not an object point. It's not an object pixel. It's a background, but we can do it. Okay, let's take. So if this is the original one, and we put the center right here. That means you need to scan. Okay, just like the convolution. Okay, you need to scan the structural element one by one. So first we put this point right here. Then for this one, you will shift to the left for 1 pixel. So this is what you got here. And then for this point, you will shift to the right for 1 pixel from the original right here. And that's the result. Okay? If we use structural element like this, we use the origin with the object point, what will be the final result? Should be, it will be the same, but all the original location should be retained, right? So it will become what? A 3x3 object. But for this one, we have two objects. One shift to the left, one shift to the right. That's what I'm saying. Usually we don't do it like this. We don't define a structural element like this, but it's legal if you have some purpose. But usually we don't define an object point as the center or the origin. Okay? So let's take a break. Okay? Let's take a break.